Hooke's law expresses a proportional relationship with the force on a spring and the elongation, meaning as you increase the force on a spring, the stretching of the spring will grow proportionally with the force. And so we write this force on a spring is equal to the spring constant, some constant, times that elongation. This is not the length of the spring total, but just the elongation. And so there should be a proportional relationship between that force and the displacement. And this is a force on the spring by Pete and the extension of the spring. If you were to write what is the force the spring is providing, it would be in the opposite direction of the elongation, meaning if I pull it in this direction, the force the spring provides is in this direction. Now there's no theory why this has to be so. This is an empirical law that Hooke saw when he looked at a spring's behavior. Let's take a look. This is zero force. This is with 200 grams. $400 grams. $600 grams. And I can see each increment of mass, or an increase in force, increased the length of the spring proportionally. And so it's very reasonable for us to write that this is a proportional relationship, and we can put in the values. Delta x. Delta x is 68 centimeters, or 0.68 meters. And what is the force on the spring? Well, if we make a force diagram of the spring, we have the force of gravity, mg, pulling down, and it's in equilibrium. The vector sum of the forces equal mass times acceleration is equal to 0. The force provided by the spring must be equal and opposite. What was it? That was 600 grams, or 0.6 kilograms times gravity, 10 meters per second squared. That's 6 kilogram meters per second squared is 6 newtons. And so now I can find the spring constant. The spring constant is equal to the force divided by delta x. This is about 9 newtons per meter. What does that mean? Well, with 6 newtons, I stretched it 0.7 meters. And this means it will stretch a meter for every 9 newtons I put on it. You want to stretch it 1 meter, you need 9 newtons. 2 meters, you need 18 newtons. Now it's true this proportionality doesn't continue forever. You may run into a point where the spring begins to deform and you reach an area of irreversible, inelastic extension. And then ultimately it's going to break. And the force that it provides is 0. But here is the linear regime, and we can use this. Now we also recognize this is a wonderful way to store energy, right? I pull it, and it stores the energy, and then I can release it and turn it into kinetic energy, and then ultimately potential energy, and then back to kinetic energy again. What's the stored potential energy in a spring? Well, I know from the work energy theorem, the potential energy stored in the spring has to be the work that I put into it. And I know work is force times delta x. In the same direction, it's a dot product. So this isn't hard. I can just say it's the force times the displacement, and that's equal to, oh right, it's equal to the force when I pull on this is equal to k delta x, right, times delta x. And that's k delta x squared. That's wrong. It's actually 1/2 k delta x squared. Why is that? Because the force wasn't equal to kx the whole time I was pulling down. Right? the force in the beginning was 0, so this work was very little compared to this work down here. And so what we can say is, sure, the force in the beginning was 0, the force at the end was kx. The average force is going to be 1/2 kx. The average force is going to be 1/2 kx. Another way to look at this is let's do the work little by little, and we can say, oh yeah, the little bit of work is equal to force dot the little bit of x, and we integrate it, is the same as finding the area under this triangle. And we can see, yeah, it's just base times height times 1/2, and there your 1/2 comes. Or we can just do the integral. That work is the potential energy stored in the spring, and that's force, that's the integral of force dx. But the force at any given x is kx dx, and you know that gives you k, the constant, times 1/2 x squared. Again, 1/2 kx squared. So let's do a calculation. Let's say I take one of these 200 kilogram masses and I extend the spring 1 meter. How high does the mass go? We start with the spring elongated, and that has potential energy, and that turns to two things. It turns to kinetic energy, but also gravitational potential energy. And then it turns only to gravitational potential energy as it gets to its highest point. So we start with the elongated spring, and the potential energy stored is 1/2 kx squared. And when I write that, I realize it's delta x. And that transitions to some gravitational potential energy when it's up here moving. And we recognize this height is actually equal to that delta x, plus this kinetic energy. And the final potential energy is mgh final. So we could solve this quadratic equation to find the velocity at this point. Then we can solve this equation and find the final height. Okay, so I solved this and then separated this into two parts. And here the mass cancels. And so I get newtons per meter times meter squared, as a newton meter is a joule, canceled with kilograms gives me meters squared per second squared. And then you subtract off this gravitational potential energy term to get 4 meters per second. That's the speed it's moving upwards. How fast is that? Think about that. That's a light jogging speed. To find the final height that it gets to when it stops and there's no kinetic energy anymore, we set this final potential energy to the initial potential energy of the spring, and we multiply these two. We get a 2 in the denominator. That makes a 1/4. This is 7. 7 times 1/4 is 1 3/4. And units, newtons per meter, meter squared, I get a newton meter. And here I have a newton, a kilogram meters per second squared. A newton meter divided by a newton gives me a meter. So it stops at about 1 3/4 meters from here. So here is 1 meter, and then it goes up another 3/4 meter. That's what we measured, but you couldn't see it. So you can see we have L0, the relaxed length, and then the stretch length of 1 meter down to here, and then 1 meter elongation, and all right, nice, that's science.